Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are in the second module of this course, that is process management. And within this module, we are trying to understand how does the operating system manage the CPU by providing this abstraction of a process, right? And within this second module, currently we are on the third topic, that is system calls, exceptions and interrupts, right? So within this topic, through a series of videos, we'll try to understand what are the different ways of communication between the process and the operating systems, right? All three of them, except system calls, exceptions, and interrupts, all of these are communication mechanisms between the process and the operating system. And currently, we are focusing on the system calls. We'll spend some time on the system calls, right? So in the previous two videos, we have understood what exactly are system calls, right? We know that these are in a way they look like function calls, and they are mechanisms via which the user process can request certain services from the operating system, right? In this video, I want to talk about behind the motivation of system calls. What happens if we do not have system calls? When you understand what happens when you do not have system calls, then you will be able to properly appreciate why exactly do we need such a mechanism. Why should there be the case that the user process should request the operating system, right? Why cannot we do things directly, right? So in this video, we'll try to understand why exactly do we need the system calls. So without further ado, let's get started. So let us now try to understand why exactly do we need the system calls. So as you can see, I have a simplified version of the compute stack here. So at the very bottom, we have the hardware. This is the hardware interface. And on top of the hardware, there is the operating system. And this is the system call interface. So I have removed the programming libraries and the user interface application for the sake of simplicity. Okay. Right. So here you can see the user applications are interacting with the system call interface directly. So now let us try to understand what happens if we so basically you see what is going on here. For every important thing that the user process wants to do, it has to request the operating system. It is not allowed to do a lot of things, right? It is forbidden to do a lot of things on its own. It cannot directly access any piece of hardware. Okay, it has to go through the operating system. It has to make a request to the operating system, and this has some overhead, right? So now we'll try to understand why is there a need for such a mechanism where for anything that the user application, not anything, but for most of the important things that the user application requires to do, it has to request the operating system. And the operating system, when the system call is invoked, it is the operating system which will take care of the operation on the behalf of the user application. So let's imagine a case when we do not have the operating system, right? We are doing all together away with the operating system. So user applications are allowed to directly access the hardware. Okay. Now there is no requirement for system calls. Anything that the user application wants to do, it is doing on its own. Is this scenario possible? Definitely yes, but there are several challenges with it. So now let us discuss what are the challenges when we do not have the system call interface or even the operating system itself. Okay. So there are many challenges. I have listed down the most important ones. So when we do not have the operating system, so the first two problems that you see, the complexity and the inefficient point, right? So we studied that the fundamental responsibility of the operating system is to make the computer hardware easy and efficient to use. So if you do not have the operating system, then it will be very difficult to use the computer hardware, right? This is where the complexity comes into the picture. And we have discussed about these 2 points in great detail in the video where we define the operating system, define the responsibilities of the operating system. So it will become very difficult for a programmer to write programs directly on the hardware. The first thing, we have removed the operating system altogether, right? The other thing is that the operating system does a careful resource management and ensures that all of the computer hardware resources are used in an efficient manner. So that efficiency goes out of the picture. You have removed the operating system itself. User applications are doing whatever they wish. So there would be no coordination between the different user applications. There would be no central entity to manage all of this, right? So it will be grossly inefficient, right? So this was about the two crucial changes that we have when we remove the operating system itself. The third thing, it would be very non-productive, right? For every basic thing that you would have to do, it will be like reinventing the wheel, right? You'll have to write your file handling yourself, your memory management yourself, right, process handling yourself. So all of the things that the operating system creates for you, all of the abstractions that the operating system creates for you to make it easy to use the hardware, you'll have nothing for yourself. Everything that you want, all the features that you have now, that is what we take for granted from the operating system, all of those features you'd have to implement yourself. It would be like reinventing the wheel again and again. All of the difficult tasks you have to do for writing each of your programs, right? So it will be very non-productive if you do not have the operating system into the picture. So till now we have talked about what would happen if the operating system itself goes out of the picture. But let's say there is some mechanism in which we have the operating system, but we do not have the system call interface. We do not have a request mechanism, right? So the user applications are requesting so currently the user applications are requesting the operating system to do things on their behalf. But let's say there is a way in which they do not have to request the operating system, and they can go ahead and use the abstractions themselves. That would be somewhat non-practical. Let's just see the case when the user applications directly use the hardware. What is the problem apart from complexity, inefficient, and non-productive? All of these are non-fatal reasons, so these reasons are okay, right? But the point is that if the user applications are directly allowed to use the hardware, then the system would be on the verge of malfunctioning. It would be a dangerous thing. It is not about just complexity or inefficiency and productivity. If user applications use the hardware directly, then the system would cease to function properly. So let us discuss some examples of what are the things that can go wrong. There are several things that can go wrong if user applications are directly allowed to use the hardware. So let us see some examples of what all could go wrong if the user applications directly use the hardware instead of going through the system call interface, right? The system call interface is a systematic way to use the hardware, but if that is not in the picture, let's see what all can go wrong. So let us take the first example, that is of disk access, and let us see what all can go wrong if the user processes are allowed to access the disk directly. Okay, so here is an example. This is the user process. Here we have the operating system. Here we have a hypothetical disk, and we can think of the disk as a sequence of blocks. Okay, so here we have the disk with 10 blocks from 0 to 9, and there are two files, file A and file B, on our disk, right? So now we are going to see how the operations take place in the presence of the operating system and in the absence of it. Okay, so let's say the user process makes a request. It is asking that I want to write two blocks to file A. So the file A is currently on the disk addresses 3, 4, and 5. Now when the operating system receives such a request, it will do many things. First of all, it will verify whether the user process is even allowed to access file A or not, right? It will verify the permissions, right? It might be the case that the user process is not allowed to access file A. Here you can see the operating system is acting as a barrier. It is acting as a safeguard. Okay, so the user process, in order to it will make a system call. It will make a system call and ask the operating system to write two blocks to file A, and the operating system will do this following checks. Then it will see whether there is enough space in the disk, and if there is enough space on the disk, then it will properly allocate the two blocks, and then it will write the two blocks on the disk in an efficient way. Okay, so here you can see, let's say the operating system allows this operation first of all, and then it carries it out. The blocks 6 and 9 are now added to file A. Initially it was just 3, 4, and 5. Now 6 and 9 are also part of file A. So two blocks have been appended or written to file A. Now let's see, let's take another case. Now let's take an example when the user process try to do something which it is not allowed to. Let's say the user process is saying, I want to write to blocks 6 and 7. Instead of saying I want to write two blocks to file A, it is directly trying to specify disk addresses. First of all, it is not allowed to do so. And then the other thing is that you can see this address 7 belongs to file B, right? Okay, we can still consider writing to address 6, but you can see address 7 is allocated to file B. Basically, if this operation is allowed, if this operation is permitted, then we are overwriting the contents of another file, which is not a right thing to do, right? So the operating system will not allow this operation. It will not permit this operation. So you can see here the operating system is not only making things easy and efficient, it is also acting as a safeguard against things which the user process should not be allowed to do. Okay, but let's say there is the operating system is not there, and the user processes are directly allowed to use the hardware. They can directly do whatever they want. Okay, so in this case, what happens is that the user process goes ahead and writes directly to block 6 and 7. and you can see the contents of file B are overwritten and lost. So this is something which should not have happened, right? If we have a system which is something like this, then this system will cease to function properly. This would not be a usable system. Users will soon give up on such a system, right? So you see, the operating system is not only there to make it easy and efficient for you, it is not only making things productive for you, it is also acting as a safeguard against things that should not happen in a computer system. A computer system has several users, multiple processes, and if we do not have such an entity to check against such things, if user processes are directly allowed to access the hardware, then many things can go wrong. So this is an example of a restricted operation. So such operations should be restricted in nature, right? So the reading and writing directly to the disk, you can see what all can go wrong if this operation is not restricted. So we'll see that these are the kind of operations that are done by the operating system on behalf of the user processes. These restricted operations, which if not restricted can lead to a unintended behavior, those are part of the system calls. Now, instead of allowing the user process to directly do these things, the user process will request the operating system. The operating system will first of all verify if this is a legal operation, and then it will carry it out on behalf of the user process. So you see, you're trying to see the motivation behind system call. It's not just about ease of use or efficiency or productivity. It is about correct system behavior. Okay, we'll take one more example and see what are the other types of restricted operations in the system. What are the kind of operations that should be done with the vigilance of the operating system. So the second example that we are going to take is that of memory allocation. So previously we talked about the disk. We saw how if the user applications directly use the disk, how the things can go wrong. Now let's look at another piece of hardware, that is the memory, right? So here we have a kind of a similar example. Here we have the user process, this is the operating system, and this is the DRAM or the physical memory. Okay, and again I'm assuming it is 10 bytes long, and there is some data at these addresses. Okay, now the user process makes a request to the operating system that I want to allocate 2 bytes. Those 2 bytes could be anywhere, it just wants to allocate 2 bytes. So the operating system will first of all check the memory, whether there is enough space available for this allocation, whether this allocation can be allowed, right? So the operating system figures out, okay, there is a lot of space on the memory and it can allow the allocation of 2 bytes. So you can see it allocated the 2 bytes at these locations 0 and 1 based on some policy. Okay, so this is how the operating system is taking care of the allocation of memory on behalf of the user process. Now let's take another example. Now the user process is requesting that I want 10 bytes instead of 2 bytes. Now it is making a larger allocation request that is for 10 bytes. And as you can see, the total size of this hypothetical memory is 10 bytes, and we cannot proceed with such an allocation request. We do not have enough space, right? Even if we have enough space, the operating system might not want to allocate the full DRAM to a single user process, because it will be like a monopoly. No other user process will be allowed to run. So even if there is space, the operating system might not allow such a big request. Okay, so what the operating system does, it declines such a request. This is the way in which the operating system safeguards the memory. It has to ensure that the memory is shared by all the processes in the system. It is not just this single process that has to use the system. So first of all, there is not enough space in the physical memory, and even if we have, we do not want to allocate all of the physical memory to one single user process. Such a request should not be allowed, and that is what the operating system does. It declines this request. Okay, now let's see what happens if the operating system is not there in the picture. So you can guess what would happen. The user process can just go ahead and use all of the physical memory for itself, right? There is no one to stop this user process from using the using any location in the physical memory. There is no operating system in the picture. So you can see this is again a restricted operation. Such operations which kind of use the hardware, which interact with the hardware, are sensitive in nature, because if the user processes are allowed to do things on their own, then the system will become unusable. User processes can be written in a malicious way, and then it will make the system unusable. So you can see this is like a city with no government, right? We have talked about the operating system as a government in a city, right? The city can be thought of as the computer system. The government can be thought of as the operating system, right? We have talked about this analogy in the earlier video where we defined the operating system. So you see, if so the computer hardware resources, these are precious in nature, and they have to be shared between all of the user processes. It's not just one process that has to use these hardware resources. These hardware resources are required for execution by all the processes, and they have to be managed in a proper way. It's not just about ease of use or efficiency. It has to be used in a way so that all of the user processes can coexist in the computer system. So if the operating system is not there, if the system call interface is not there, then there is no guarantee of a usable system. It is kind of a situation, it is like a situation of anarchy in a city. There is no one to control the city. The system goes, the city goes in a state of anarchy, right? So you see the rationale behind having system calls. It is a protected way and a very controlled way of using the system, so that the computer system is actually usable by multiple users and multiple processes, right? So we have seen through several examples, right, what can happen if you do not have the system call interface. So we need the system call interface. We need the operating system to be in control of the hardware, right? The user applications must request these operations via the system call interface, whichever operation that they want to perform, right? When I say whichever operation, basically all of those forbidden operation, all of those restricted operations that the user application wants to perform, it can make the request via the system call interface. And by invoking the system call, it can request the operating system to perform that operation or provide that service for the user applications, right? So this was a basic idea of why do we need the system call interface, because without it, things will not be in the control of the operating system. So the system will become unusable. System call mechanisms provide a very safe and proper way, a controlled way of using the system. Okay. So another analogy that I have for making you understand about system calls in a better way is to think of the operating system as a guardian or a parent, and the user process as a child. Okay, so you can think of the relationship between the user process and the operating system as that of a parent-child relationship, right? So let us understand this with some examples. So there are certain activities that are there in our daily life which involve a certain sense of responsibility to, in order to accomplish them, right? For example, let's say driving, right? Driving, or let's say cooking, or the handling of expenses. All of these are activities which require you to be sensible, which require you to be mature and responsible. And that certain level of maturity we can expect only from parents, right? Kids, let's say very small kids, do not have the understanding of how they should go about doing these things. These are the we should leave these things to adults, right? So for example, if you take the case of driving a car, you should know the traffic rules. Also, it is kind of not safe to allow the kids to drive the car. So if you leave things, if you leave such responsible activities in the hands of the children, then things can go wrong. For example, if the kids are allowed to drive, if underage kids without license, without training are allowed to drive the car, then they could make an accident and there could be loss of lives, right? We do not want such a situation to happen. So we want the driving to be in the hands of the parents, right? So the kids can request the parents that we want to go to this place, or we have to go to school, we have to go to the market, and the parent can take care of the task and do it on behalf of the child, right? Just like the operating system, whenever the user process has to do something which is restricted, it requests the operating system to carry out those operations on behalf of the user process. So you can see here, driving is forbidden for the children. They are not allowed to drive, because if they are allowed to drive, then things can go wrong. Similarly, the case of cooking, here you have to handle with sharp equipments like knife. There is the fire. When you're cooking, you have fire, right? And if you're using oven, then there is electricity. So all of these equipments, cooking is it can be hazardous if you do not do it properly. So we cannot leave the task of cooking for the children, but nonetheless cooking is necessary because we require food. Children need the food. So when the children need the food, they can request the parents to do the cooking for them. They do not need to request, but the parents will do it for them, right? So the needs, the need for cooked food that is there for the children, that has to be fulfilled by the parent, right? Just like the case of the user process and the operating system. Otherwise, if we let the task of cooking in the hands of children, then you can imagine what all can go wrong. The house could be on the fire, right? And one final example that I have is that handling of expenses, right? When you have money, you would want to spend it in a responsible way. Otherwise, you will go out. Otherwise, you will run out of money, right? If children are given all the control of the money, then they would buy the next thing that they like. They can buy anything that they want. We do not want such reckless spending. So spending of money is another responsible task. And so whatever needs that are there for the children, it could be to buy certain objects, certain things, all of that monetary requirements of the children have to be fulfilled by the parents, because they are responsible. If we leave the control of the money with the children, then it can go all wrong, right? There's a high chance of things going wrong. So you can see the same situation in the computer system. The computer hardware is a precious resource, and if it is not used properly, if it is if the control of the computer hardware is left solely in the hands of the user processes, then malicious processes can take over the control of the system. The system can become unusable. That is why we restrict a lot of operations, most of the operations that are related to the computer hardware, and we do not allow the user process to directly interface the hardware. Now it is the operating system which has the full control of the computer hardware, because it is a trusted piece of code, right? We trust the operating system. The operating system is written by another entity, by so it is the only piece of code that has been written so that the system can be run in a proper way. So all of the user processes, whatever are the requirements of using the computer hardware, they will request the operating system via the system call interface, and the operating system will take care of those requirements on behalf of the user processes. The operating system will first of all validate whether such a request should be allowed, and if it has to be allowed, then only it will carry out it on behalf of the user processes. So this is how the things work in the computer system. Just like in our daily lives, the interaction between the user process and the operating system is very much like a child parent relationship, right? So guys, this was it for this video. In this video, we discussed why do we need the system calls, right? In the previous video, we understood what are the system calls, but here we understood what exactly is the mechanism, what exactly is the motivation behind having such a mechanism where the user process has to request the operating system for most of the things that it has to do, right? So we saw some analogies also. We saw some examples of what are the things that can go wrong if the user processes are directly allowed to use the computer hardware. And then finally, we discussed the relationship between the user process and the operating system as being similar to that of a parent-child relationship. So guys, this was it for this video. Thank you very much for watching, and I will see you in the next video. Thank you.